In section 9.1, we're going to be solving a general linear system of equations in integers. So that's our primary goal, just to find all integer solutions to an arbitrary system of linear equations. And the method that I'm going to introduce is to diagonalize an integer matrix via elementary row and column operations. Okay, so long back we solved a single linear equation in two variables, ax plus by equals c. And now I want to turn to a system of k linear equations and n unknowns, and I can represent it like this. So we have the coefficients a sub I, j, and I have a collection of integer constants on the right-hand side, and we can rewrite this system as a matrix equation. So it's ax equals b, where a is the coefficient matrix, a k by n matrix with integer entries, x is a column matrix of variables, and b is a column matrix of constants. Now already when we solved a single equation in two variables, we saw a big difference between finding integer solutions and what you did back in linear algebra or college algebra, just finding all real number solutions. And so we're going to find the same difference here for a system of equations. We can't just use Gaussian elimination like we did back in linear algebra. The problem there is you can have fractions. You can divide and do types of arithmetic that would lead to non-integer solutions. So we have to be very careful in just sticking with whole numbers as we do these operations. So our strategy is to make an appropriate change of variables so that the system becomes diagonalized. So I'm going to let x be qy, where q is our change of variables matrix, an invertible matrix over z, and y is a column matrix of new variables, y1 through yn. And then after we make that change of variables, we want to end up with a very simple system of equations like this. And I call that a diagonal system, where each variable just appears in a single equation. So d1 times y1 is some b1 prime, d2 times y2 is some b2 prime, and so on. And that system is trivial to solve. So by inspection we can see that this first equation here is solvable if and only if d1 is a divisor of b1 prime, in which case y1 equals b1 prime over d1, and so on. So you get a very simple system to solve when it's diagonalized. Okay, now before we diagonalize the system, let's review a few facts about elementary row and column operations for matrices. So there are three types of elementary row operations. You can multiply a row by -1, and why am I just restricting to this one value here? It's because we want it to be an invertible operation over the integers. The only unit in the integers, well, there's 1, but you would never multiply a row by 1. The only other unit is -1. So this is a valid elementary row operation. The second operation is we can add an integer multiple of one row to another, and I'll indicate that like this. So this means add lambda times row I to row j. So if we have this matrix here, 1, 2, 3, 4, and I want to go 2 times row 1 added to row 2, I'd leave row 1 alone, and then I'm multiplying row 1 by 2 and adding it to the second row. So 2 plus 3 is 5, 4 plus 4 is 8. And that's an invertible operation because to undo it I would just subtract 2 times row 1 from row 2. Now notice if you did Ri plus lambda Rj, that would not be an invertible operation unless lambda happened to be plus or minus 1. So you can't do a row operation of this type. You always have to add a multiple of one row to another row. you can also just swap two rows. And this just means switch rows I and j right here. So those are the three elementary row operations. There are analogous elementary column operations. And then we define an elementary matrix to be a square matrix obtained from the identity matrix by a single elementary row or column operation. So how do we use these elementary matrices? So let's recall what happens when we multiply by an elementary matrix. So if E is an elementary matrix obtained by a particular row or column operation, and E times A is defined, then E times A is the matrix obtained by performing the same row operation on A. And A times E is the matrix obtained by performing the same column operation on A. So when you put an elementary matrix to the left of a matrix, it does a row operation, and when you put it to the right of a matrix, it's performing a column operation. So let's look at an example of this. Okay, so here's my elementary matrix, and let's think of this as being 2 times row 1 added to row 2. And then I'm going to put a matrix A, B, C, D right here, and look at the effect. So you would get A, B, the first row is left alone, and in the second row we take 2, 1 times AC, so you get 2A plus C, and you get 2B plus D. And so what have we done to this? This is our A matrix here, and this is the E matrix here. We have taken the A matrix and simply added 2 times row 1 to row 2. So it's performing the row operation. Or if we put it on the right, what do we get? We get A plus 2B, B, C plus 2D, D. And so what have we done now? So this is A, E. We have done a column operation where I've taken 2 times the second column and I've added it to the first column. So 2 times column 2 added to column 1, and that's exactly the way you'd think of this elementary matrix E in terms of being a column operation. You've taken the identity matrix and added 2 times the second column to the first column. So then if we perform a sequence of elementary row and column operations, so let's say we have E1, E2 through EJ are the row operations, and F1 through FK are the column operations, then what happens to the matrix A? So we start with A, we do the first row operation E1, and then maybe a column operation, and then maybe another column operation, and then maybe another row operation, and you go back and forth, and eventually you get this matrix after performing all of the row and column operations. And note that it's a matrix of this form, P, A, Q, where P is the product of the row operations, Q is the product of the column operations. Okay, let's give a name to this concept. So if A and B are K by N matrices over the integers, we say that A and B are equivalent matrices, and write it with a tilde. A is equivalent to B. If there exist invertible matrices P and Q over the integers, so invertible over Z, the inverse is also a matrix with integer entries, we have PAQ equals B. That type of relationship we just saw on the previous slide. And a few notes about this. So plainly, equivalence of matrices as defined above is an equivalence relationship. symmetric, reflexive, and transitive. 2, if A is equivalent to a diagonal type matrix, which means a matrix whose entries are 0 for I not equal to j, then D is called a diagonalization of the matrix A. And 3, from what we saw in the previous slide, A and B are equivalent matrices if and only if there is a sequence of elementary row and column operations that transforms the matrix A into B. So if B is PAQ, then the matrix P is performing the row operations, and the matrix Q is performing the column operations. So that's a nice way to think of matrix multiplication. When you're multiplying on the left, you are doing row operations to the matrix on the right, and when you're multiplying on the right, you're doing column operations to the matrix on your left. So here's the key theorem in this section. I call it the diagonalization theorem. So let A be any k by n matrix with integer entries. Then A is equivalent to a diagonal type matrix. That is, there are invertible matrices P and Q such that PAQ is a diagonal type matrix. So that'll be the key theorem for diagonalizing our system of linear equations. Proof. So we may assume A is a non-zero matrix and then perform a row swap if necessary to put a non-zero row into the first row. Then what I do is I look at the entries in the first row and I perform the Euclidean algorithm to produce the GCD of those entries. So we did this back in an earlier section. So what does that mean? You're adding a multiple of one column to another, and you keep repeating this. That's what you're doing in the Euclidean algorithm. And so this can be accomplished by a finite sequence of elementary column operations, and you end up with a first row which will have the GCD in the left position and all zeros to the right of it. Then in the next step, we look at the first column. So at this point you'll have a D1 and a 0, 0, 0, and then you'll have entries underneath it. You focus on the first column now, and we ask, does D1 divide every entry in that first column? And if not, what I'll do is I'll divide that entry by D1. So let's say that D1 doesn't divide the entry AK1. And so I say AK1 is some quotient times D1 plus a remainder R1, where R1 is strictly smaller than D1. And then I perform a row operation. I'll take minus Q times row 1, add it to row K to produce the entry R1 in row K. And then I swap rows 1 and rows K to put R1 into the 1, 1 position. So then you've got an R1 here. And note R1 is smaller than D1, but the problem is we have now possibly introduced non-zero quantities into that first row. So we have to repeat step 2. Again, we perform the Euclidean algorithm to turn the first row into a D2, 0, 0, 0, 0, 0, and this time D2 is smaller, strictly smaller than D1. And then I repeat step 3. Does D2 now divide every entry in the first column? And if not, we go on repeating steps 2 and 3 as many times as necessary, and we keep reducing the size of that entry in the upper left corner. So eventually we get down to 1, or eventually we get down to a point where that entry is a divisor of every entry in the first column. So let's say we have D000 in the first row. where D divides every entry in the first column. Then I just start subtracting appropriate multiples of D from the entries in the first column via elementary row operations. So if this entry is 3 times D, I just go minus 3 times row 1, add it to row 3, and I eliminate this entry. So by doing these elementary row operations, we get all zeros in the first column, and I haven't altered these zeros here because I'm not going to do a row swap at this point. Well, we now have a matrix of this sort. So now we just proceed by induction. Now I focus my attention on the n minus 1 by k minus 1 submatrix right here. And we do the same procedure. And note, when I'm performing the row and column operations on this submatrix, I'm never going to alter the zeros up here or the zeros over here. And so now we just proceed by induction. Proceeding by induction. We complete the diagonalization. So not only is this proven the theorem, it's actually given us the algorithm for how we're going to solve a system of equations. All right, let's do a couple examples. So let's show that the matrix 6, 4, 2, 8, 10, 4 is equivalent to the diagonalized matrix 2, 2 with a bunch of zeros. And let's find the matrices P and Q that put it into diagonal form. Okay, so I just start by writing down my coefficient matrix, 6, 4, 2. Yeah, let's go ahead and 6, 4, 2, 8, 10, 4. And if I want to keep track of the P and Q, I need to keep track of my row and column operations. So I'll put the identity matrix over here, and I'll put an identity matrix down here. And that's just a device for keeping track of the row and column operations. Okay, so what's the first thing we do? We just focus on our matrix A up here. I want to perform the Euclidean algorithm to get the GCD up into the 1, 1 position. Well, in this case, it's very easy to see that 2 is going to be the GCD, and so let's just swap columns 3 and columns 1 in my first step. So column 3 is 2, 4, 0, 0, 1. Leave column 2 alone. 6, 8, 1, 0, 0. So notice that this matrix down here is the elementary matrix indicating a swap of columns 1 and 3. And I haven't done anything on the row operations. Okay, what's next? Next I want to subtract minus 2 times row. No, these are column operations still. I want to eliminate these entries right here. So minus 2 times column 1 added to column 2, and minus 3 times column 1 added to column 3. So 2, leave the first column alone, minus 2 times this added to here, minus 2 times 1 added to here, minus 3 added to here, so 0, minus 12 added to 8 is negative 4. Is that right? So I had minus 12 added to 8. Yep. No change there, no change here, and minus 3 there, and no change up in this corner. Okay, then I want to eliminate the 4 right here. So negative 2 times row 1 added to row 2. This time we do a row operation. So I leave row 1 alone. And 0, 2, negative 4, negative 2, oops, that's a 1 there, negative 2 added to 0, and I haven't done anything to our columns. And then finally we want to eliminate this negative 4 right here. So what do we do there? 2 times column 2 added to column 3. So first column I leave alone, 0, 0, 1. Second column I leave alone, 0, 2, 0, 1, negative 2. And the third column, 0, 0. 2 doesn't change. 2 added to 0. Negative 4 added to negative 3. Negative 7. And no row changes here. And there you have it. So we have obtained the diagonal matrix D right here. The matrix down here is tracking all of the column operations, so that's Q. And the matrix over here is keeping track of the row operations, so that's P. So P, A, Q gives us this diagonal matrix. All right, so now let's talk about diagonalizing our system of linear equations. So I want to solve AX equals B, where A is a K by N matrix. And let's suppose that P and Q are the invertible matrices over Z that diagonalize the matrix A. So PAQ is a diagonal matrix where D has some entries along the main diagonal, D1, D2 through DK, and all of the entries off the diagonal are 0. Then I let X equal Q times Y. So now I make my change of variables, where Y is a new column matrix of variables. And let's look at what happens to the system of equations. So we started with AX equaling B. I multiply both sides by P, and what we're doing here is just doing row operations. I'm doing some elimination by simple row operations when I multiply by P on both sides. And then I use the associative law to say that PAX is PA times X. Substitute in that X is QY. And then use the associative law to regroup the parentheses. And now I have PAQY. But PAQ is the diagonal matrix. And so I get D times Y is P times B. We have now obtained the system dy equals PB, and let's write that dy equals B prime. And as a matrix equation, here's the D matrix. Here's my column matrix of variables y1 through yn, and this is the B prime matrix on the right-hand side. And that system is very easy. This is just D1 times Y1 is B1 prime, D2 times Y2 is B2 prime, and in general DI times YI is BI prime, as Y goes from 1 to K. So let's say that the first R entries of the DIs are non-zero, right here, and then DI equals 0 for I between R and K. So plainly, this system right here, so now we're looking at this diagonal system, will be solvable if and only if di is a divisor of bi prime, for I going from 1 to r, those are where the di's are non-zero, and bi prime must equal 0 for any value of I between r and k, because there you'd have a di to be 0, and you would need 0 equaling 0 for this equation to be solvable. And if we have a solution, the solution would have yi to be bi prime over di, for I going from 1 to r, and all of the remaining yi variables are free variables. I going from r plus 1 up to n. So free variable means the ti's are arbitrary integers. And then finally, the solution to the original equation is obtained by bringing back the x variables. X is q times y. Okay, let's do an example of solving a linear system. So here's my linear system with some constants a and b on the right-hand side. And I want to find for what values of a and b the system is solvable. So let's start by forming the coefficient matrix for 6, negative 2a, 2, negative 8, 10b, and augment it with an identity matrix right here. Now notice when we're solving a system of linear equations, I don't need to find the matrix P. It's not relevant. We just have to find the change of variable matrix Q, which corresponds to the column operations. So I form this augmented matrix. And then I want to put a 2 in the upper left corner, so I'll just swap rows 1 and 2. I could also have swapped columns 1 and columns 3. So 2, negative 8, 10, b, 4, 6, negative 2, a, and leave this all alone. Okay, then I want to clean up these two entries here. So what do I do for that? I do a column operation, 4 times column 1 added to column 2, and negative 5 times column 1 added to column 3. So what do we get? I leave the first column alone, like that. Negative 8 added to, 8 added to negative 8 is 0. 4 times 4 is 16, added to 6 is 22. 4, 1, 0. And then negative 5 times the first column added to the third column. 0, negative 22, negative 5, 0, 1. And b and a have not changed. Okay, next I want to clean up the 4 right here. So we do minus 2 times row 1 added to row 2. So leave row 1 alone. 0, 22, minus 22, negative 2b added to a. And this matrix hasn't been touched. Okay, then we want to clean up this submatrix, so I want to get rid of the negative 22 here by adding the second column to the third column. So column 2 added to column 3. So leave the first column alone and the second column alone. So 2, 0, 1, 0, 0, 0, 22, 4, 1, 0, 0, 0, 4 added to negative 5, 1 added to 0, this, and the b and the a minus 2b are left alone. Okay, so we have now diagonalized our matrix, so that's D, and the diagonal system is what? It's going to be 2 times y1 equals b, 22 times y2 equals a minus 2b. And the Q matrix, that's the change of variables matrix, is sitting right down here. So, when does the system have a solution? Okay, let's rewrite what we just found out. So 2y1 is b, 22y2 is a minus 2b, and Q is our change of variables matrix. So the system is solvable if and only if 2 is a divisor of b and 22 is a divisor of a minus 2b, in which case the general solution in terms of y's would be y1 is b over 2, y2 is a minus 2b over 22, and y3 is a free variable, where t can be any integer. And then bring back x, so x1, x2, x3 is the matrix Q, times y1, y2, y3. So y1 plus 4y2 minus y3, y2 plus y3, and y3. And so we get x1 is y1 b over 2 plus 4 times y2, which is a minus 2b over 22, minus y3. x2 is y2 plus y3, so a minus 2b over 22 plus t, and x3 is t, where t is an arbitrary integer. And that is a nice way to describe the general solution set. I wouldn't even go ahead and multiply out these two things, because you really want to realize that this is just a whole number here. Right? We're assuming that 22 is a divisor. That's just some whole number, and this is a whole number. I would just leave them intact like this.